Okay, so the last part of 7.2 is going to create a different type of volume. So the first two things we did is we took a representative rectangle and we spun it about an axis. Okay? We either spun it, the two things were we spun it around the x-axis, or I should say we spun it around the horizontal line, or we spun it around the vertical line. Horizontal line worked in terms of x, vertical line worked in terms of y. Sometimes that line shifted off the axis, but again, still remembering top minus bottom or right minus left, not bad. And it created some weird shapes. So today we're going to do something called a cross section, which takes a different approach. It doesn't revolve things to generate volume, it stacks things up together. Okay, so if you think about one way to think about it would be, if I wanted to create a cylinder, I could create a cylinder by taking a rectangle and spinning it. You all can visualize that, right?
Sure.
I could also create a cylinder by stacking a bunch of, let's say, quarters on top of each other, right? So if I take a bunch of discs and stack them up on top of each other, I would get a cylinder. You with me?
Yep.
Okay, we can generate a cone, for instance, by spinning a triangle around an axis. We did that already. But I could also create a cone by stacking discs on top of each other that get smaller and smaller and smaller, right? Can you visualize that?
Yes.
Good. So what we're going to do today is that stacking idea of creating a cross section and stacking them on top of each other to get volumes. And we're not going to do anything as simple as a cylinder, because why would I do a cylinder when I can just use the formula for a cylinder? We're going to generate some weirder shapes. And I've got some cool examples of what those things are. So there you go. We're going to find volumes using cross sections. Nothing else exciting on there. We're going to start right away with this is basically what I explained. I want to start right away with the Sketchpad demo so that you can see what some of these shapes look like. Okay, so let's start with, which one are we doing first? Okay, we're going to take a base. There's two things we're concerned about. What shape is the base, and what shape are we stacking on top of the base? So this first example is going to take a base of a circle, and we're going to stack squares on top of it. Okay, and those squares in this particular case are going to be perpendicular to the x-axis. Right, so it looks like this. These are all the bases, and we'll actually have an infinite number of bases, but that gives you a general idea of what they look like. And then just to give you that cool 3D look, I'm just going to drop that down a little. Not that much, actually. Whoops. There we go. That's a little bit more reasonable. Okay. And so if I start stacking squares on top of that thing, I get something like that. And notice that the squares change in size as you get closer to the edge. Are you with me so far? How big will a square be if it's at R?
0.
0. Okay. And where will I get the biggest square? In the middle, correct. Okay. So then what happens is, since we have calculus now, we can create an infinite number of rectangles and then just stack all those infinite number of rectangles next to each other. How thick are those rectangles, by the way? Or sorry, these are squares. How thick are those squares? dx, correct. Really, really tiny. And what this is just showing is how they generate as you move across. And then what we'd like to see is what it looks like when we leave them all there, and we get that weird looking solid. And it just keeps going like that. Okay, so it looks something like that. It looks like a cylinder where you kind of carved a weird edge across the top of it. Okay. You're not going to have to draw these, by the way. That's a different class. Okay, so what can we change? We can change the base, and we can change the shape. So let's look at what happens when you take, instead of a square stacked on top of this, we stack equilateral triangles. So again, drop that thing flat, and if we sweep one of them, well, there's 4 of them, I don't care about those, you go away. Sweep one of them, and then we'd like to see what happens when it leaves it behind, and so we end up with that weird looking thing. Okay. Now the math for this is pretty easy. What's difficult is visualizing what these shapes look like. And like I said, you're not going to have to draw them. But you should be able to kind of get a general idea of what it's going to look like. Okay, so let's stop that guy. Let's do this. Let's put a right triangle as the base. And so here, if I flatten it out, I'm starting with a right triangle, and then I'm going to stack on top of that semicircles. Okay, and the semicircles in this case are going to be parallel to the x-axis. So my chords show segments. There's the chords. Now, what I want you to do before I click the button is picture what that thing looks like. All right, I'm not even going to ask you to describe it because it's too weird. But if you stack those semicircles, you get this thing that kind of, well, not kind of, it is half of a cone. Or a hemicone. Yeah.
How do you decide which way to do that?
The problem will tell you. It'll say you've got a base of blah, blah, blah. You'll see in the examples. You got a base of blah, 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 and we're going to stack blah, blah, blah shapes parallel to the x-axis, perpendicular to the x-axis, parallel to the y-axis, or perpendicular to the y-axis. It'll give you that information. Because depending on the way that you stack it, generates a different shape and a different volume. Okay, and then the last one I'll show you is a right triangle with right triangles. Let's see, that's not what I want. I don't know if I even wanted to show you this one. Yeah, so this one's stacking right triangles on top of a right triangle, and you get that little pyramid looking thing. Okay? So that gives you a general idea of what we're doing. And like I said, the math is pretty simple. Quit. Okay, we can quit now.
It's right in front of you.
Oh, thank you. Don't save. Okay. This is it. This is all we need to do. We need to figure out where we're taking slices from where to where, and we need to find the area of one slice. So the setup is easy. Some of the calculus can get a little hairy, but it's not that bad. There's no pies in here unless we use, let's say, a semicircle, but the general formula doesn't have a pie involved. Okay. Find the area of one cross section and use the integral as an accumulator to add up all those cross sections. Okay. And then the two graphics here just show you what happens if you do it in terms of y, what happens if you do it in terms of x. Okay, so really all you need out of that is the integral from a to b of ax dx, or the integral from c to d of ay dy, depending on whether we're going in terms of x or in terms of y. Still have a representative rectangle, but we got a little bit of a kicker on the back end of that representative rectangle. We also have a representative area. Okay, we good? So here's our starting problem. We've got the graph of x equals y squared as my base, and the line x equals 9 is going to generate a region. That's going to generate the base of the figure, and then stacked on top of that figure are rectangles. The width of those rectangles will change. For this problem, to make things a little bit easier, I made the height of the rectangles consistent. So it's 2 all the way across. So we're going to get, well, let's start with this. What's the function x equals y squared look like? Brian?
A C.
A C, okay? Mathematically speaking?
Yeah.
You know, it wasn't a yes-no question. It was a, mathematically speaking, what is it? It's not.
A parabola flipped.
Perfect. Parabola on its side. Okay. So we're looking at the region from that sideways parabola up to 9. And on top of that, we're going to stack rectangles. Okay, so here's our base. I drew a representative rectangle over here. It doesn't have to be over here. I could have put it over here. I can pretty much put it wherever I want, but it's going to go here. How do I know it's here? Because it says we're perpendicular to the x-axis. So hopefully you can visualize in your head that I'm going to have a rectangle sticking up out of the board here. And as I get closer to the x-axis, the width of that rectangle is going to get smaller and smaller. But the height in this particular problem is going to stay consistent, so it's going to be a flat top on that. So it's going to be like a three-dimensional parabola here. Notice what I did over here. I found that point. And you'll recall that we got done with x and y a long time ago, so now we do x comma f of x. So that point is x comma square root of x. What I need to know is the area of the cross section. So this is the new thing you're going to draw. Aside from the shape of your base with a representative rectangle, you're also going to draw the shape that we're dealing with. This bolded section is important. The representative rectangle from the base matches the base of my representative area. Gesundheit. All right, are you with me on that?
Where did the 2 root x come from?
Good. Where did the 2 root x come from?
It's this area question.
No,
Because it's height times.
it's this distance.
So you solve for like that point.
I know the distance from the x-axis up to that point is the square root of x. So therefore, this whole thing would be 2 square roots of x. Yeah, so that's the base of my rectangle.
Okay.
The height is fixed in this problem. So notice if I was doing squares instead of rectangles, I wouldn't have a 2 there. I'd have a 2 square root of x, and the rectangle would, or sorry, the square would change as you get closer. Okay, that's the hard part. If you can get that, the rest of it is easy. We're taking rectangles from where to where?
0 to 9.
0 to 9. And what's the area of that rectangle?
2
Two.
times square root of x times
Good. Also known as
4 root x.
4 root x.
2. Well, yeah.
Okay. Fairly easy integral, yes? Desi?
Wait, why was it 4 root x then?
Because it's the area of the rectangle, base times height. The base of this rectangle is the same as the representative rectangle over here. The height in this particular problem fixes it at 2, so that doesn't change. And so 2 square root of x times 2 is 4 square root of x.
Yes.
Okay. All right, any problems? Now, how can we make it more interesting? And it doesn't involve trig, by the way. Let's change the height of the rectangle. Let's not make it a rectangle. We could make it into, let's say, a semicircle. We could make it into an equilateral triangle. We could make it into all kinds of different things. Now I'm going to use a circle. And I'm going to have my sections be equilateral triangles perpendicular to the y-axis. So before I click and show you a picture, you draw a picture. Draw a picture of the base, put in your representative rectangle, and then draw your representative area. We can worry about labeling values and distances later, just get a general idea of what's going on here. By the way, what's the equation of a circle with a radius of 4 at, with the center at the origin?
X squared, the square root, x squared,
X squared
oh,
plus y
sorry,
squared
x squared
equals
plus y squared equals.
Or 16.
Which one? 4 or 16?
16.
16, good. Okay, you got it? So you should have a circle on your paper on an axis, and you should have an equilateral triangle somewhere off on the side. Something like that. I put my representative rectangle down here in quadrants 3 and 4. You could have put it up here, it doesn't matter. And then I have to have an equilateral triangle. But that we just did. And then where's my equilateral triangle? Oh. Why did I do that? Why did I solve for x?
What in terms of y?
Why?
Because perpendicular to y.
Well said, Max. Everybody hear that? I want that function in terms of y because my representative rectangle is perpendicular, or sorry, it's horizontal because it's perpendicular to the axis that we're dealing with. Okay. Let's see what we got next. There's my equilateral triangle. There's my representative rectangle. This is an important point. Does everybody understand where that came from? That 2 times the square root of 16 minus y squared. This point is the square root of 16 minus y squared comma y, right? Because we're working in terms of y now. Or it would be x comma the square root of 16 minus x squared if we were working in terms of x, but we're working in terms of y. Okay. Now we got to do a little bit of geometry. This is where things get a little nasty. Question over there.
What if it wasn't on the origin?
Then that's a whole new can of worms. Because then you've got like x minus 2 quantity squared plus y minus 3 quantity squared equals 25.
You have to find the midpoint.
You gotta do all kinds of fun things. Yeah, you'd have a center axis, which would be a line that's not the, or, yeah.
Are we doing that?
No. We can if you'd like.
No.
Okay, just thought I'd throw it out there.
Wait, I still don't understand two. 16 minus y.
Good. All right, so the question is, where did the 2 square root of 16 minus y come from? Notice that this distance is that, because it's the x value.
Okay.
And this represents the base here. That's why that's bolder than that. Or on your paper, you might want to use a red pen for that and a red pen for the base of the triangle. Okay? Everybody else good? Now a little bit of geometry. Yes, sir.
Where did the 2 come from? Yeah. Because there's 2 of them. Like on the other side?
Yeah, here and here. This distance is square root of 16 minus y squared because it's the x value. But we need the whole distance, so we double it.
It's like the diameter.
I'm sure, for those of you that had a good geometry teacher, I'm sure you all remember the formula for the area of an equilateral triangle, right?
I did.
S squared squared is 3 over 4,
Oh, of course.
right?
Was that?
Luke, you remember that, right?
Oh, sure.
Attaboy, good job. S is the length of one side, square times square root of 3 over 4.
Why?
Okay, so, you want me to
I
derive
took
it?
geometry in summer school.
Wow.
I don't
Oh, yeah, so did
understand.
Wow. Yeah, okay.
Oh yeah.
So, I could explain that to you, but I don't have the time, so jot it down.
Okay.
It comes from taking an equilateral triangle, chopping it in half. You have a 30, 60, 90 triangle where you call that side S, that would be 2S, and that would be S squared root of 3, and then taking the base times the height times a half, you end up with that nice little formula.
Yeah, didn't follow
Oh, that's easy.
So the calculus in this problem isn't bad. The geometry gets a little bit nasty because notice now I have to take this mess and put it into there because I need the area of that equilateral triangle. This shape, by the way, is going to be the same shape that we saw in the Sketchpad demo. It's that pointy looking weird shapey thing. Okay, so this isn't really that bad because when I square, I'm putting an S squared. When I put that in, I'm going to get 4 times the radicand there. So I'll take you through all that fun stuff. There I just plugged it in.
Do we have to know that?
S squared squared root of 3 over 4, that would be something you should probably know. You can do 1/2 base times height,
Mm-hmm.
but it requires that you go and do a 30, 60, 90 triangle again, so you gotta remember that, you gotta do all that. It's easier to just file that bad boy away. It doesn't come up a lot, but if it does, you're on top of it.
Are you gonna give us like area for like suggest formulas that we should know?
Oh, yeah.
for these?
Yeah. All right, so then I simplified that whole mess and got it down to that, which is not too bad. Before I click and show you, what are my limits of integration here?
Negative 4.
Beautiful, -4 to 4. I'm taking these representative rectangles from the bottom here at -4 and extending them all the way up to the top, which is at -4. Or if you're feeling saucy, you could go from 0 to 4, or you could go from -4 to 0 and double it. Okay. Or just go from -4 to 4. Sometimes there is an advantage to taking half of it and doubling it because plugging 0 in usually works out a little bit better. Okay, before I go through all the calculus, are we okay with this? Beautiful. Okay, so set up my integral there. The volume is equal to the integral of the area from -4 to 4. Now that we're talking about area and we're talking about volume, this setup is very important. If you throw an equation up there, it's got to equal something, and that equal is what's important. Put an A or a V there. Don't assume that someone looking at the problem knows what you're doing. How would you solve that integral? What's the antiderivative of 16?
16y.
16y. What's the integral of negative y squared?
Negative 1/3 y.
Negative 1/3 y cubed. Plug in negative 4, plug in 4. Okay, so there are the antiderivatives. Plug that funness in. Woo, that's good. And then simplify. On a non-calculator portion of a test, you would get this as an answer. On the calculator portion, you probably wouldn't even go through this. You'd set it up FN in to get 147.802. Okay, so again, for the remember there's a difference between the AP test and what we're doing in class. If this were a quiz or a test question, you would see in there that it would say, show your antiderivative. So I'd want to see this, then plug and chug. On the AP test itself, if this problem pops up on the calculator portion, you're not even going to bother with all this gunk. You're just going to FN int once you get that set up. Okay? Are we good?
Yeah.
So what we've seen is we started with a sideways parabola as a base with rectangles on top of it. We just looked at a circle with equilateral triangles on top of it. There are a ton of different possibilities. You can stack any geometric shape pretty much on top of any geometric shape. It's just a matter of how bad you want to make, or how difficult you want to make your life. As Mason said, does it have to be at the origin? No, we could take that circle and move it wherever we want in the coordinate plane, and we can stack whatever we want on top of it. What do you got?
So, say you have like an isosceles triangle
As a base or as a cross section?
as a cross section.
Okay.
When you're going across an axis, how do you determine which way it goes? Like, you know what I'm saying?
No.
So, alright, never mind. This is a stupid question.
Okay.
We usually move on.
You sure?
Unless we have an isosceles triangle problem like that.
And again, did you say base or cross section?
Cross section.
Cross section. The problem with an isosceles triangle cross section is you need to know more information. Do you want the top to stay consistent as the bottom gets bigger and smaller, or do you want the bottom to get, you know? So if that were a problem, you wouldn't see anything this complicated, but you might do a problem where it's got a circle as a base and an isosceles triangle whose height is twice as big as the base. Like a big, tall, skinny triangle that gets bigger as you move across and smaller as you get down to the bottom. That's a little too nasty for us. Okay. Get it? It's a cross section.
Millennium Form.
Very
Oh,
good.
yeah.
Very good. Okay.
I built the Lego.
So again, remember when you're setting these problems up, we want to know, we want to see a diagram, or I should say a graph of the base with your representative rectangle, and then you take that representative rectangle and make it the base of your representative area. Calculate the area of the figure of the representative area, and then integrate. Okay. Bob,
You target.
Never mind.
glad I could help.